Hi, this is example number 9 of chapter 13, section 13.5. We have a car with a mass with 800 kilograms. It's traveling over a hill that has a shape of a parabola. When the car is at point A, so we have to imagine our car right here, right? So it is at point A, so it has traveled all along. Has a velocity of 9 meters over second and a rate of change of speed is 3 meters second squared. So we know that the velocity is tangent to the trajectory, and we know that that rate of change of the velocity is also tangent to, so we have the acceleration, tangent acceleration. And we are asked to find the resultant force and the resultant friction force, the car at that point. So the first thing we have to do is to decide which coordinate system we want to use, and since we are given the tangent velocity and the tangent acceleration, we like to use coordinates normal and tangent components. So what do we do for the solution? The first thing what we're going to do is draw our free body diagram of that car in that position. So I'm going to draw it as a little box. Our coordinate system is tangent and normal component. This has to be perpendicular, right? This is a perpendicular, normal. And what do we have as forces for our free body diagram? We have a normal force, and we have a friction force, and then we have our weight acting on our, and the weight, as you know, is always vertical because our gravity is always vertical. And so as we know, we see, if this is tangent and normal, we actually want this angle. This is the vertical, and this is the same angle. So the angle that is relating our weight with our tangent and normal component, we name it theta. So we know that this angle right here is theta. Then want to draw our kinetic diagram. And in our kinetic diagram, we will have our tangent acceleration, our normal acceleration. We know that our tangent acceleration is the rate of change of the speed, and that value is given. And we know that the normal acceleration is the velocity, which is given over the radius of curvature, but the radius of curvature is not given. So let's apply our equations of motion. Our equations of motion, you know, force is equals mass times acceleration. So we add our forces in tangent directions, and which forces do we have? So we want to add forces in here. We see that this is negative the frictional force, the normal is perpendicular, and the component of the weight in that direction, plus the weight times sine of theta. So those are my external forces, and those forces are equals to the forces in my kinetic diagram, which is equals to mass times the rate of change of the velocity. So this is my first equation, and right here I can see that what I want to find is the frictional force. So let me solve for frictional force first. So this will be frictional force will be equals to the weight, which is 800 times 9.81 sine of theta, right, minus 800, and our rate of change of speed is 3 meters second squared, meters per second. So let's name this equation equation number 1. And what is the unknown in this equation? Theta. We do not know theta. but we know the shape of that parabola. So we will use the shape of that parabola to find that angle theta. My second equation of equilibrium, of motion, actually, not equilibrium, is equals to the normal, in the normal direction, it will be negative the normal, right, because it goes opposite to my, where I put that positive, my coordinate system, negative plus weight cosine of theta. And that's equals to my mass times velocity squared, which is given, over the radius of curvature. So, if I solve for n, I have that will be my weight, 9.81 cosine of theta minus my mass times the velocity 9 squared over the radius of curvature. So this is my second equation. Equation number 2. Equation number 2. So what are the unknowns in these two equations? My unknowns will be theta and rho. So I need to find, in order to find f and n, which are what we are being asked, we need to find theta and rho. So let me change here to find theta and rho, we will use our equation that describes the path that that car is driving over, right? So, as we know, tangent theta is slope. And what is the slope? The slope will be the derivative of this equation, right? So it will be the derivative of that equation, which is 1 minus x squared over 6400. And that's equals to, the first one is a constant, so I have 20 times 2x over 6400. And I want to evaluate that in x equals 80 meters. Because here, that distance from 0 to my point A is 80 meters. When I evaluate that, I get the value of, this is a negative, so this is a negative, negative 0.5. So theta will be tangent to the negative 1 of negative 0.5. Since I'm finding this is a negative because this is a negative slope, but since I'm finding this angle, I can take the absolute value, and that will give me 26.6 degrees. So this is the angle that I will use to find my f. So right here with this angle, I plug it in here and I can find how much is f. To find the radius of curvature, to find n, I will use, you remember from the theory, that the radius of curvature will be as the equation of 1 plus the derivative of the equation square to the 3/2. And the second derivative, we already know that dy dx is negative 0.5. We need to find dy over dx second derivative, right? And that will be, I will derive this expression again, and that just gave me negative 40 over 6400. If I evaluate that in x equals 80, that gives me a value of negative 0.00625. So having negative 0.5 and negative 0.00625, I plug those numbers here and I get for x equals 80 meters, I get that my radius of curvature is equals to 223.6 meters. So I have the second value that I needed. Now, well, using equation 1, I found that f is equals to, because I will plug the value of the angle, that's only I need for finding f, and f gives me a value of 1,114 newtons. And using equation 2, I found that the normal, plugging in the value of the angle and the value of rho, it gives me a value of 6,728 newtons. So we found the resultant normal force and the frictional force having the slope, the velocity, and the acceleration.